sklearndecompositionMiniBatchNMF. Description: MiniBatchNMF implements a slightly faster version of the NMF algorithm that is better suited for large datasets. It uses mini batches of samples to update the model, which can significantly speed up the training process. Inputs: X. The data matrix to be decomposed. This is a 2D array of shape n samples. N features, where n samples is the number of samples and n features is the number of features in P. Data. N components, the number of components to extract. This is the dimensionality of the latent space that you are projecting your data into. Outputs. Components. This is the components matrix. This is a 2D array of shape n components. N features. Each row represents a component, and each column corresponds to a feature. Reconstruction. This is the reconstruction error of the model. This is a scalar value that represents the difference between the original data matrix and P. Reconstructed data matrix. Steps. The algorithm initializes the components matrix randomly. The algorithm iteratively updates the components matrix and the coefficient matrix using a mini batch of samples at a time. The algorithm stops when the reconstruction error converges or when the maximum number of iterations is reached. Metrics. Reconstruction error. This is the difference between the original data matrix and P. Reconstructed data matrix. A lower reconstruction error indicates a better fit of the model to the data. Sparsity. This is a measure of how sparse the components matrix is. A sparser components matrix is often more interpretable and easier to understand. Visualization plots. Reconstruction error vs. iteration. This plot shows how the reconstruction error changes over time during training. This can be used to assess the convergence of the algorithm. Components matrix. This plot can be used to visualize the components learned by the model. Each row of the components matrix corresponds to a component, and each column corresponds to a feature. Heat map of the components matrix. This plot can be used to visualize the sparsity of P. Components matrix. Fine-tune parameters. N components. This is the number of components to extract. This parameter controls the dimensionality of the latent space that you are projecting your data into. A higher value of n components will result in a more complex model that can capture more of P variance in the data, but it can also lead to overfitting. In it, this parameter controls how the components matrix is initialized. The default value is NNDSVD, which uses a non-negative double singular value decomposition. You can also use random to initialize the components matrix randomly. Solver. This parameter controls the solver used to update the components matrix in P. Coefficient matrix. The default value is CD, which uses the coordinate descent solver. You can also use mu for multiplicative updates. Alpha. This parameter controls the sparsity of the components matrix. A higher value of alpha will result in a sparser components matrix. Beta. This parameter controls the smoothness of the components matrix. A higher value of beta will result in a smoother components matrix. Uncertainty methods. Bootstrap. This method involves repeatedly sampling the data with replacement and training P model on each sample. This can be used to estimate the uncertainty in the components matrix and the reconstruction error. Bayesian NMF. This method uses a Bayesian framework to estimate the uncertainty in the components matrix and the reconstruction error. Challenges and fixes. Challenge 1. The algorithm can be slow to converge, especially for large datasets. Sample use case that resulted in challenge 1 when training on a large dataset with millions of samples and thousands of features. The algorithm may take several hours or even days to converge. Fixes to challenge 1. Use mini-batching. This involves using mini batches of samples to update the model, which can significantly speed up the training process. Use a more efficient solver. The CD solver is generally faster than the mu solver. Use a smaller number of components. This will reduce the complexity of the model and speed up the training process. Challenge 2. The algorithm can be sensitive to the initial values of the components matrix. Sample use case that resulted in challenge 2. When initializing the components matrix randomly, the algorithm may converge to a local minimum that is not the global minimum. Fixes to challenge 2. Use a good initialization method. The NNDSVD initialization method is generally better than random initialization. Run the algorithm multiple times with different initializations and select the model with the lowest reconstruction error. Challenge 3. The algorithm can be prone to overfitting. Sample use case that resulted in challenge 3. When the number of components is too high, the model may overfit the training data and perform poorly on unseen data. Fixes to challenge 3. Use regularization. Regularization can be used to penalize complex models and prevent overfitting. Use cross-validation to select the optimal number of components.